gamma rays can be something to worry about. They're at the far end of the electromagnetic spectrum, beyond X-rays. They have the shortest wavelength and highest frequency of all, but like the rest of the spectrum, they travel at the speed of light. A gamma ray is extremely small, the same size as the nucleus of an atom, smaller than the rest of the electromagnetic spectrum. They can cause extreme damage emitted by unstable atoms, whether in an atomic bomb, from radioactive waste, or even as cosmic rays from dying stars. But they can also be used to treat brain tumours.
The gamma knife produces a highly focused radiation dose inside the head. Each beam of gamma radiation is relatively harmless on its own, but where all 200 coincide and cross, you get a very highly focused dose of radiation to that area.
This patient, Conrad Graham, has come to the Cromwell Hospital in London for the procedure.
The only symptom I have really is lack of balance, but this is very unpleasant. The best way of describing it is it's as though I've drunk half a bottle of whiskey and it's with me all the time. I've read a bit about it, so I know what to expect. It's just a matter of damage limitation. They're going to stop nasty things that might happen if this wasn't done.
The treatment begins with his consultant fitting a rigid frame.
Fitting the frame involves, first of all, injections of local anaesthetic, 2 at the front, 2 at the back.
You all right, Mr. Graham?
And then the fitting of the frame, which is done via 4 pins which screw into the head.
Good, I'm happy.
The local anaesthetic makes it at least bearable. The patient then goes to the MRI scanner. The MRI scanner gives us very fine cuts through the patient's head, and we can then place those onto the treatment planning computer, and we can simulate the radiation doses that we're going to give the patient. This small outline here in red is the tumour, which measures maybe 2 centimetres across. This is a tumour that's very inside the patient's head, and it's very, very difficult to operate on. You can see the tumour here showing the area that's going to be treated. The next stage in treatment is the patient going into the gamma knife itself. The patient lies on the treatment couch and their frame is attached firmly inside the collimator helmet. Now, the collimator helmet focuses 200 beams of gamma radiation in a very fine focus, which has an accuracy of better than ½ millimetre. The collimators are made out of tungsten, which is a very dense material which absorbs radiation.
We're going to go out the room now, okay? We're watching you all the time.
No one is allowed inside the room once the gamma knife doors are opened.
That's as far in as you're going to go. The treatment's just starting now, okay?
Yep.
One of the advantages about gamma knife is the low risks involved with the treatment. With conventional surgery, you've got the risks of general anaesthesia, you've got the risks of infection because you're opening up the body, and then you've got the risks of actually cutting through healthy brain to get to the tumour itself. So the risks can be significantly higher with conventional surgery. With the gamma knife, you've got very low risks because the radiation around the tumour is at a very, very low dose.
We'll sit you up there. Sit you up slowly.
In the majority of conditions treated with gamma knife surgery, we'd expect the success rate to be in the region of 90%. So we're extremely confident that the patient's tumour will be controlled and they'll have no further problems from it.
The ionosphere that surrounds the Earth provides a life-saving barrier, stopping extreme damage due to X-ray radiation. X-rays are between gamma rays and ultraviolet on the electromagnetic spectrum. Their wavelength is slightly shorter than ultraviolet, however they have a higher frequency. An X-ray is the same size as an atom. It's very small, but bigger than a gamma ray. In medicine, the X-rays produced can be controlled so that their benefit outweighs their risk.
Plain film simple X-rays are used really as a quick diagnostic tool. So in the A&E setting, they're very, very useful. So at someone falling over, banged their knee in this case, they can get in a plain film X-ray very quickly and whether they've broken any bones within the knee.
With modern digital X-rays, you're able to see soft tissue as well as bone.
This is done by X-ray beam hitting a phosphor plate. Cassettes then put into a machine where the laser light scans over the plate and causes the electrons to release their energy in a form of light. That form of light is then converted into a digital image, which you can see on the screen behind me. Joe Smith, please. Unfortunately, there's always risks involved with ionising radiation, so that's why we always try to make sure that it's justified. Joe?
9 September 85.
A plain, simple X-ray uses about 4 times the background radiation dose a patient would receive just by being out in the street, or a chest X-ray is the same as the background radiation they'd receive from one transatlantic flight. That's it. And just relax your shoulders down.
Hello, Mr. Brown.
But X-rays aren't just used to show us what's going on inside the body. They can also be used to destroy cancerous cells.
They found out that I got cancer by me having several bouts of an infection in the bladder. I came to the hospital, saw a consultant who did lots of tests, scans and the like, and they discovered through that I have got the cancer of my prostate.
Critical to the successful treatment of prostate cancer is the treatment plan.
This is an example of a treatment plan produced by a treatment planning radiographer. And they have ensured that the tumour has been covered by the high-dose region represented by the blue line, whilst the rest of the patient receives a much lower dose, which is represented by the light blue line. The lower dose is associated with less risk.
The X-rays inside a radiotherapy machine, which is used to treat cancer, have much higher energy than a standard X-ray. Inside here, there's a linear accelerator which speeds up electrons. The faster they travel, the greater the energy of the X-rays produced. These pass through a dense metal template which restricts the X-rays. So they only go where the radiotherapist has decided they're needed.
There are checks and counter-checks to ensure that at all stages the patient is accurately aligned under the treatment unit.
This attention to accuracy means healthy tissue is largely avoided, so the process is incredibly safe.
The actual treatment took no more than 2 minutes. There was no pain, no sensation, nothing. You didn't even know that there was a machine on apart from hearing it go buzz. And the buzzing, I'm a great counter, so I was counting every time the buzzes went, and it was about 11 or 12 seconds per day. The actual treatment time was very, very short.
Every radiotherapy patient then has to wait 6 weeks to find out just how successful their treatment has been. The ultraviolet light in the sun's rays gives us a tan, or causes us to burn. Ultraviolet sits between visible light and X-rays on the electromagnetic spectrum. Its wavelength is slightly shorter than visible light, but it has a higher frequency. An ultraviolet ray is the size of a protein molecule inside your body. One extraordinary use of ultraviolet light is in laser eye surgery, where the cornea is reshaped painlessly to improve eyesight.
The amazing thing about ultraviolet light at 193 nanometers, which is the frequency that we use, is that it is completely absorbed by corneal tissue. Cornea is the window at the front of the eye, the watch glass, if you like, through which light passes. The advantage of all this energy being absorbed into this very small area of the surface is that the laser, every time it pulses, that energy is absorbed, and only in the order of 1/4 of 1,000th of a millimeter of tissue is removed per pulse.
Alex hopes this procedure will mean he can throw away his glasses.
I've been wearing glasses since I was about 10 or 11. Wearing contact lenses was a temporary solution, but it was quite, couldn't go swimming with them, and obviously quite fiddly when you're younger. Getting infections in your eyes and things like that is obviously not too good. The main advantages I can think of having corrective surgery would be that it frees me up. I don't have to wear glasses or contact lenses anymore.
Okay, I'm looking up at the O a few lines up.
Okay.
Sharper 1 or 2.
Oh, 2 is much clearer.
And 3 or... Alex has a prescription of -5. That means that he is focused at 1/5 of a meter away. So at 20 centimeters, everything's clear for Alex. We're going to need to remove something like 80 thousandths of a millimeter from the center of his cornea. It's going to be very easy. The procedure itself takes 3 minutes or so. Straight ahead of the green flash. Concentrate on the green. The way it works is that we take the cornea and we make a very, very thin shaving. That shaving is brought back. The laser is then used to shape the bed, and then the flap is put back.
A red light is used to track the eye.
All surgery, and particularly surgery which you choose to have, that means you don't have to have, it's very important to consider the risk and benefit balance. The risk, therefore, has to be relatively low because glasses work very well and they're very low risk. The modern alternative is to have it corrected permanently by one procedure. The risk of a little bit of damage to the vision, the chances are probably 1 in 10 to 20,000. Okay, Alex, you've had perfect LASIK and it will be healed in 3 hours. It's over before you know it. The refocusing of the eye is practically instantaneous. And so you get what is called a wow effect. All right, so remember what it looked like where you laid down 10 minutes ago?
Yeah. Well, yeah. Blurry.
All right, open your eyes and check your vision now.
Yeah, it's amazing.
Everything that we see is due to the visible section of the electromagnetic spectrum. It sits at the spectrum's center and is the only section that our eyes are sensitive to. Each color has a slightly different frequency and wavelength, but they all travel at the same speed, 300 million meters per second. Within the visible spectrum, the red light, next to infrared, has the longest wavelength and lowest frequency, whilst violet, next to ultraviolet, has the shortest wavelength and highest frequency. They're the same size as the bacteria inside our stomach.
We do 2 principal things with visible light. The first is diagnostic therapy, and we use our endoscopes to look into people's tummies, and we get a video picture of the inside of the tummies, and that's all with visible light. The second thing we do is to use visible light in a therapy called photodynamic therapy, or PDT. Thanks, Barry. Good morning. Have a seat.
Great, thank you.
The patient that we're going to treat today has got a precancerous condition of his esophagus called high-grade dysplasia in Barrett's esophagus. Now, he has approximately a 1/4 chance of going on to develop cancer in the next 2 years. And up till recently, the only available treatment has been surgery to remove part of their esophagus, which contains the diseased area. Surgery contains very high risks in that between 1 in 20 and 1 in 10 people that have the operation don't survive.
The procedure out today is photodynamic therapy. The patient, Mr. Barry, has been given a drug that makes his skin extremely sensitive to light, both on the inside, including his esophagus, and the skin outside.
Photodynamic therapy is actually the combination of us giving the patient a drug that makes them sensitive to light before the treatment, and then shining a powerful laser light at the diseased area of the body that we wish to destroy. The combination of the drug and the light makes those cells die, and hopefully when it heals, the disease is no longer there and the patient is cured. You'll feel sleepy in just a minute. No, Mr. Barry, just relax. Pop your tongue down for me. Well done. There's almost 100% survival following photodynamic therapy. Photodynamic therapy has been shown to reduce the risk of developing cancer following treatment by 50%.
The red light we use has a wavelength of 633 nanometers.
So the laser fibre is now inside the patient, directed at the diseased area of the esophagus, and because he already has the drug in his body that makes him sensitive to light, the combination of the two will make those diseased cells die. Well done, sir. It's all over now. Just going to take everything out. Even though photodynamic therapy is a lot safer than surgery, it does carry some risks, and the first is sensitivity to light for a prolonged period of time, and the patient is quite seriously sensitive to light for up to a month after treatment, and it can cause a sunburn-like reaction. The second risk is a risk of narrowings of the gullet that would prevent food from passing from your mouth into your stomach. They could need to be stretched, and stretches, while normally safe, do carry a very small risk of creating a hole in the esophagus, which would be very serious indeed.
Eamon Barry's very successful, leaving no damage to his esophagus and a greatly reduced risk of developing cancer. Infrared is between the visible and microwave section of the electromagnetic spectrum. Like all electromagnetic radiation, it travels at the speed of light, but its wavelength is longer than visible light and it has a lower frequency. It's the same size as a human hair. Infrared is given off by anything warm, including our bodies. This can be detected by special cameras.
Infrared thermal imaging was first developed for night vision purposes, to enable us to see targets and people in the dark. So it's used a lot by the military, by the Army and Air Force, and also for night vision from police helicopters. But it's also very useful in medicine to look at the temperature across the human body from the skin surface. The patients that we mostly see at the Royal Free Hospital have a condition called Raynaud's phenomenon, and typically they report white and blue fingers when they go out in the cold winter weather, and they're very slow to become warm again.
Jan thinks she might have Raynaud's, so has come to the Royal Free Hospital in London to find out.
I first noticed, I suppose, when I was in my 20s, and it sort of got progressively worse over the years. It affects my feet and my hands.
Come on in.
I can sort of do something about my hands, but my feet are the really worst part for me. And they go completely white and dead. Although they're sort of numb, they're also painful at the same time.
So I'm going to place a board, if I may.
The first thing to do before starting the test is to take the temperature of Jan's hands. Testing using an infrared camera is called thermography.
We call it the cold challenge test with thermography, and the hands of the patient are placed in cold water for 1 minute to make the fingers slightly cold. Perfect. I'm going to monitor how long you're in there for, so that you only remain in for 1 minute. And then we use thermography over a period of about 10 minutes to see how quickly the fingers are becoming warm again. And we'll start recording again with the thermal camera. What we can see here on the screen after your hands have been in cold water is that the fingers have become quite blue, especially at the tips of the fingers, which are the more sensitive areas of the hand. What we want to do now in this area is see whether the fingers warm up again over about 10 minutes. So here we are 10 minutes after the cold challenge, and you can see there's really been very little rewarming of the fingers over the entire 10-minute period. If you place your hands in cold water normally, we find that the fingers are warm again in 5 or 6 minutes in a healthy person. But in a Raynaud's phenomenon patient, we can often find it takes more than 10 minutes for the hands to become warm.
The infrared images confirm that Jan has Raynaud's. With this information, she can receive the right treatment. Microwaves are an essential part of our everyday lives, either to connect us to our friends via our mobiles or to heat up a quick meal. They sit between infrared and radio waves. So they have a fairly long wavelength, from around 1 to 5 centimetres, and a low frequency. Only radio waves are longer and lower. You can think of them as the size of a finger. Microwaves have a very important use within medicine. They allow us to produce the high-energy X-rays that are essential in radiotherapy treatments for cancer, as standard X-rays can't penetrate deep into the body. High-energy X-rays by a linear accelerator, which brings electrons and microwaves together. An electron has a negative charge. Other negatively charged particles, like another electron, will repel it. But a positive charge, like a proton, will attract it. When an object is suddenly given a positive charge, the electron will speed up towards it. And if, when the electron reaches that object, it then becomes negative, while at the same time a further object becomes positive, the electron will be attracted to that further positive object and will speed up towards it. This is exactly what happens in a linear accelerator, but around 1 billion times a second. This matches the frequency of microwave radiation, so that's what's used to switch the positive and negative charges. The electrons can then generate high-energy X-rays. It's incredibly precise work which treats cancer in thousands of patients every year. Radio waves carry our favourite sounds and soap operas through the air into our homes. They sit at the end of the electromagnetic spectrum, just beyond microwaves. They can have an extremely long wavelength, sometimes several kilometres in length, but at their shortest, they're around 1 metre. They also have a very low frequency. The shorter radio waves, which are used for television, are around the length of a person. But radio waves can be as long as a hillside. They're the longest waves of the electromagnetic spectrum. Radio waves have been put to use in magnetic resonance imaging, MRI, to produce extraordinary internal images.
MRI is invaluable at looking at the different areas of the body. In particular, it's really good for looking at brain, and it's very good at looking at joints, bones, the liver, and generally just any areas where there might be a tumour. When the patient arrives in the department, we have to ensure that the patient is safe. The MRI scanner is a powerful magnet, and therefore we must ensure that the patient does not have any metal objects on them or within them.
The scan does make quite a lot of noise, so I'm going to give you some earplugs to put in.
A small percentage of patients are claustrophobic, and that can prevent them from actually having the scan. It is quite a big problem for us, so we have to make sure that the patient's really comfortable.
The MRI scan gives a three-dimensional picture of the inside of the human body, showing fluids, fat and bone.
Depending on the area that we're looking at, the scans can vary between anything between 3 minutes and 7 minutes. They are very susceptible to movement, and therefore we must ensure that the patient doesn't move at all.
The magnet in the MRI scanner causes all the protons in the body to go into alignment. These are spinning at a constant frequency. A radio wave is pulsed into the scanner, which causes the protons to move out of alignment. When the radio wave pulse is switched off, they go back. The MRI scan provides a detailed image of the inside of the human body, so the patient's doctor can make a painless diagnosis and decide on any treatment.